بسم الله الرحمن الرحيم. أهلا وسهلا بالحضور الكرام، أهلا وسهلا بالجميع. Let me first start by welcoming our committee members, starting from our Dr. Muhannad Al-Shraide. Dr. Muhannad Al-Shraide is an associate professor at the Jordan University of Science and Technology, the Civil Engineering Department, and Dr. Muhannad teaches courses in hydraulics and graduate level courses in conveyance systems. So we very much appreciate his presence today, and we value his input and highlights on this work. Thank you, Dr. Muhannad, for being here today.
Thank you very much.
I also would like to thank Dr. Munjid Al-Sharif, our previous colleague at the Jordan University of Science and Technology, who is currently at the German Jordan University, the Water and Environment, Water Resources Department. We value very much your presence, Dr. Munjid. We understand how busy you are. Thank you very much for being here today.
My pleasure. Thank you very much for inviting me.
And last but not least, the co-advisor on Ahmed's thesis, Dr. Christian Klassert, who has been my colleague and have been working together on various projects for the past 5 years or so, who is also very knowledgeable in the water resources in Jordan, in water management in Jordan in general. Dr. Klassert has, to introduce him, he has a PhD in economics from the Leipzig University, and his PhD focused on Jordan, especially on the modeling of hydroeconomic systems of the formal and informal water markets in Jordan. Currently, Dr. Christian is a postdoctoral researcher at the Department of Economics at the Helmholtz Center for Environmental Research at Leipzig, Germany. Thank you for being here today, Christian.
Thank you very much for the invitation.
So Ahmed, I'm gonna give you maybe a minute or less just to introduce yourself. We know that you are finishing your master's from JUST, but maybe a little bit about your background, and then you can start with your presentation. And as we discussed, as you start with the presentation, I suggest that you, as you start with the presentation, you give yourself 20 to 25 minutes at most, so that we allow time for the committee to evaluate your work. Go ahead.
Okay, thank you very much. Well, first of all, my name is Ahmed Al-Kabsi. I have graduated from Civil Engineering Department from Sana'a University in 2014. After this, I worked as a civil engineer for almost 4 years in a construction company in Yemen. After this, I joined the master program in Jordan University of Science and Technology. Nowadays, I joined a short-term research in Helmholtz Center for Environmental Research, funded by the German Academic Exchange Services, the DAAD. Yes, and now I am about to graduate from this master program. Let me first welcome you all to my presentation, the committee members, Dr. Samer, Dr. Christian, Dr. Muhannad, and Dr. Munjid. Thank you very much for your time today. I also would like to welcome the attendees. And today I will present my master thesis titled Water-Energy-Nexus: Energy Consumption for Jordan's Main Water Conveyance System based on Water Evaluation and Planning Model. I have divided my presentation into 5 main parts: the introduction, the objectives, the methodology, and here I will focus on 4 main points: the data used for this study, identifying the main water conveyance system, developing water balance WEAP model for Jordan, and finally designing the future scenarios. After this, we will have a look at the results and discussion, and finally the conclusion and the future work. I would like to start my presentation by giving some facts and figures about the water and the energy sectors in Jordan. Well, Jordan suffers from severe situation in terms of water and energy. In terms of water, as we can see in figure 1, that almost all groundwater aquifers in Jordan are over-abstracted. In terms of energy, we can see in figure 2 that the energy production in 2020, 93% of the energy production was imported, while only 7% was the domestic production. Figure 3 shows the energy intensity of water supply in different regions, and we can see that the energy intensity for water supply in Jordan is 8.01 kilowatt hour per cubic meter, which is high comparing to other countries from different regions. The energy intensity is the amount of energy required to deliver a cubic meter of water from the water source to the demand site. It is called virtual energy consumption, and it is also called specific energy consumption. Looking at figure 4, we can see the electrical energy consumption by sector in 2018, and for the agriculture and water pumping, the percentage was 15.34. Here comes the Water-Energy-Nexus approach to better understand the relationship and the interaction between the water and the energy sectors, to understand how much water is being consumed for the energy production, and on the other hand, how much energy is consumed in the different water cycle stages. Figure 5 shows that the energy contributes almost in all the water cycle stages: the conveyances, the treatments, the wastewater collection and treatments, and so on. Well, this study has 3 main objectives. First, to build a water balance model using WEAP tool to obtain the water transferred in the main conveyance system. Secondly, to provide a special estimate of the energy requirements for the main conveyance system for the duration between 2015 until 2050. And lastly, to estimate the total energy intensity of the water supply. Moving on to the methodology, we can see in figure 6 a chart flow for the methodology, starting by data collection and preparation. The data was collected from different authorities in Jordan, such as MIAH Water Company, the Ministry of Water and Irrigation, some published reports such as the National Water Policy. Using this data, a schematic was created using ArcGIS. This schematic identifies 3 main points, 3 main elements, which are the water sources, the demand site, and the transmission links. Using the data and the schematic, the WEAP model was created using the WEAP tool. After this, the future scenarios were developed based on 4 main factors, which are the population growth, living standards, the supply enhancement, and demand management. After this, the energy was calculated through 3 main elements, which are the energy equation approach, the transferred water that has been obtained from the WEAP model, and the digital elevation model. And lastly, all the results were visualized and illustrated using ArcGIS. Starting by the data used for the study, the population was obtained from the population of the kingdom from the Department of Statistics, from the General Census of Population and Housing Result 2015. A per capita water supply by governments was obtained from the Environmental Statistic Reports 2014 and 2015. The ArcGIS water network was obtained from the MWI, and the groundwater extraction limits was obtained also from the Ministry of Water and Irrigation. With regards to the future water projects in Jordan, it was obtained from the National Water Policy 2016 until 2025 and from the MWI. The digital elevation model for this study was obtained from the United States Geological Survey USGS website, and with the regards to the monthly variation, it was obtained from MIAH Water Company, and also some data was obtained from MIAH Water Company with regards to the energy consumption for some conveyance lines, such as Zara Ma'in and Zay to Amman links. Here on the slide, I would like just to clarify how the main conveyance network was identified. We can see in figure 7a, the Jordan's water supply network ArcGIS file. In this ArcGIS file, we have the data with regards to the names of the pipelines, the diameters, and also there is another file with regards to the water facilities in the network. In figure B, we can see the overlap between the schematic that has been developed and the actual pipeline network. And the final schematic is illustrated in figure B and figure C that identifies the water sources, the demand sites, the junctions, and the transmission links. Moving on to the WEAP modeling, well, the WEAP tool is a computer tool that is being used for the integration, management, and planning for the water resources. This software was developed by Stockholm Institute for Environmental Research in the late 80s. The first step to for this modeling is to insert the schematic by inserting the nodes for the water sources and the demand sites, and then linking these nodes by the transmission links. The step after this is inserting all available data for this schematic, such as the population growth rates, the water capacities, the water losses, and after inserting all the data, we go to the developing the scenarios, and lastly to run the model. Well, how the scenarios were developed, as I have mentioned before, that 4 main factors were used to design these scenarios: the population growth and the living standards as an external occurring factors, and the supply enhancement and demand management as a management scenarios factors. The supply enhancement was represented by the water project development for the future, while the demand management was represented by the water loss reduction. So 5 main scenarios were developed: the reference scenario that represents the built as usual scenario, the continuous same water use behavior of the past. This answers a question: what if the same water use continues even when there is more water supply or more water projects will be applied? Because as I have noticed from the reports published from 2015 until 2019, there is no any change in or reduction in the water use behavior, especially in those governorates that use high water use rates, such as Aqaba or Karak. We have the management scenario one that suggests that the population growth is high, the living standards is high, there is water project development, and there is water loss reduction. Here, the water loss reduction was based on the recommendations from the National Water Policy, which is to reduce the water loss from 52 to 30%. In the management scenario 2, it's almost the same as the management scenario 1. The only difference is the population growth in this scenario is moderate. And lastly, the pessimistic scenario, which represents the worst case scenario, where there is no any supply enhancement or demand management. Moving on to the results and discussion, I would like to start by giving this water transfer validation. Here what have been done is that a comparison between the simulated results and the actual results for the water supply for some transmission links were made. The data was obtained from Yahuna Water Company for some transmission links, and the error bar here is 10%. As it can be observed from the figures that the error was lower than 10% in most of the months. It exceeded the 10% in some months, but for the overall duration, it is lower than 10%. For the transmission link from Amman to Zarqa, it exceeded the 10% especially in the year 2020. This slide shows a comparison between the unmet water demand for the developed scenarios. Looking at the base year 2015, the unmet demand was 132 million cubic meter for all the scenarios. Looking at the pessimistic scenario in orange, when there is no any water supply enhancement or demand management, the unmet demand will keep increasing to reach almost 800 million cubic meter by the year 2050. Looking at the reference scenario in blue, we can see that when adding a future project, future water project, this tries to keep this unmet demand almost in the same level, around 130 million cubic meter. And the significant drop was by the year 2030, when almost all the projects operates in full capacities. We can see in management scenario 1 that when adding the decrease in the water losses, this leads to a significant decrease in the unmet demand, and it reached to 0 by the year 2030. It continues in low unmet demand, but it starts to rise again, to increase to almost 400 million cubic meter by the end of the duration. It should be mentioned here that the population growth is high in this scenario, but when looking at the management scenario 2 in green, where moderate population growth is used, that there is also a significant decrease in the unmet demand. This could represent the best developed scenarios, but these figures can summarize that in terms of water supply, Jordan suffers from severe situation. This slide gives almost the same results as the previous slide. The only difference is that this slide elaborates more on the unmet demand, in which governorates it exists. So there we have 3 main governorates where this unmet demand exists, which are Amman, Zarqa, and Irbid. From this slide, the results of the energy calculations started. We can see in table 3 that the calculated energy consumption for Zay to Amman link was 332 gigawatt hour, while it was 176 gigawatt hour for Zara Ma'in to Amman link. Based on the actual data that has been obtained from Yahuna Water Company, the error of the energy consumption was 2.29% for Zay to Amman link, while it was 12.89% for Zara Ma'in to Amman. Looking at figure 16, it provides a sensitivity of changing the velocity value on the calculations error for Zay to Amman link. It should be mentioned here that the velocity that has been used for the calculations was 1.3. It was between the range from 1 to 2 meters per second as per the recommendations of hydraulic box to avoid sedimentation and erosion. So I tried to figure out how much this error will be when changing this velocity, and it can be appeared from the figure 16 that the error did not exceed the 10%. Figure 17 provide a profile graph for Amman to Zarqa transmission link from the ArcGIS. We can see, the reason I put this figure here is that some results for some transmission links for the energy calculations were negative, and this only occurs when the water moves from high elevation to lower elevation. So this result was checked by the ArcGIS, and it is also was checked by email from engineer Dua Abu Ghunaymat, one of the engineers that works for Yahuna Water Company. Here on this slide, we can see a special energy consumption for the whole network. As we can see here, what should be highlighted from this slide is that the higher energy consumption was in 3 transmission links, which are Zay to Amman, Zara Ma'in to Amman, this is Zay to Amman link, Zara Ma'in to Amman link, and the first part of the DC to Ma'an project. And the highest energy intensities was in Zara Ma'in to Amman and Zay to Amman with 5.59 and 4.96 kilowatt hour per cubic meter. The total energy consumption for the base year was 1,484 gigawatt hour. But does the total energy intensity of water supply come only from conveying the water? The simple answer is no. We can see in table 5 range of energy intensities for water use cycle segments. We see that we have 5 water cycle segments: the water supply and conveyance, the water treatment, the water distribution, wastewater collection and treatment, and wastewater discharge. I tried to calculate these values for the energy intensity for the first 2 water cycle stages, because as it can be observed, they are the prominent water cycle stages looking at the numbers. So the energy intensity for the water supply and conveyance was 7.05 for the water supply and conveyance, and it was 0.5 for the water treatment. The total energy intensity was 7.55 for the whole system. And according to the Energy in Water Sector 2019 report, this value was 8.01 kilowatt hour per cubic meter in the year 2015. Figure 19 shows a special energy consumption for the whole system in different years. For the reference scenario, the years 2020, 30, 40, and 50. We can see that for the years 2020, there is no big difference because there were not more water project capacities that were added to the system. From the year 2030 and 40 and 50, almost all the projects operate in full capacities. That's why the energy consumption rates significantly. And the higher energy consumer here was the Red Sea project. This figure has been done for all the scenarios, but what can summarize what happens in the whole system and in the all scenarios is figure 20 that provides the total energy consumption for the whole system. Looking at the base year 2015, the total energy consumption was almost 1,500 gigawatt hour. Looking at the year 2020, there is no big difference as I have mentioned earlier. But looking at the reference scenario, we can see that by the year 2030, there is a significant increase in the energy consumption, especially when adding all the projects and the Red Sea project. This energy consumption keeps almost in the same level until the end of the duration. And the reason for this is that there is no more water to be transferred. So we can conclude that the scarcity of water supply somehow constrains the energy consumption requirements. The lower energy consumption was in the management scenario 2, where the population growth were moderate and there is water project development and also water loss reduction. To make long story short, this study has tried to provide an insight of the energy requirements for Jordan's main water conveyance system. Zayt Amman and Zara Ma'in Amman links had the highest energy intensities. The results shows massive future energy requirements, which will be almost doubled from 1,500 gigawatt hour to 3,100 gigawatt hour. The total energy intensity for the water supply system in Jordan was 7.55 kilowatt hour per cubic meter. And lastly, however, the Red Sea project could reduce the unmet demand by the year 2030 to almost zero. It is high energy consumer. With regards to the future implementation, there are mainly 3 future implementation for this study. First, an intensive energy auditing will be required to provide elaborate insight and optimization alternatives, especially for those critical links where we have high energy consumption or high energy intensities. Secondly, conducting a multi-criteria site selection analysis using ArcGIS could be done to highlight the best sites for the renewable energy alternatives, such as the solar energy or wind energy. And lastly, the findings of this study can be used for Jordan's Water-Energy-Nexus policies to focus more on reducing the energy requirements in the water sector in the future, because all the previous water or energy policies did not focus mainly on this part. This slide brings us to the end of my presentation today. Thank you very much for your time, and now I would like to welcome, and I would be happy to answer your questions and to listen to any comments to improve this study.